we'll do that using the so-called E-script. So, as I said, the right-hand side of update equations contain curls. And the curl of F is right? So the curl contains a bunch of space derivatives. So we'll approximate these space derivatives using the finite difference method. Okay, so this approximation is called finite difference method again. And we'll do this on E-script. So what is E-script? It is actually one of the most important concepts in FDTD. So it corresponds to the leapfrog fashion of time discretization. It is a space version of that. So this is one discretization cell in space. So the space is filled with these boxes, and this point is oh, sorry. Yeah.
Sorry.
I usually don't make this mistake because I hate making that mistake. Thank you a lot. So, yeah. And this point is I plus 1 delta x, j delta y, k delta z. And all the other points are evaluated similarly. And this is where Ex is defined. And this is where Ey is defined. And this is where Ez is defined. And we draw a line dots are at the center of the faces. So this is where hx is defined, and this is where hy is defined, and this is where hg is defined. And again, I'll use a shorthand notation.
H field is defined on the front surface of the
Yes,
field,
yeah.
or the center plane.
So the H field here, Hx, is defined at this point here, and Hg is defined at this point here. The center of the bottom face, and Hy is defined at the center of the front face.
Center of the front face.
Yes. So if you use this shorthand notation, Ex is actually defined at I plus a half j k, and Ey is defined at I j plus a half k, and Eg is defined at I j k plus a half. And Hx is defined at I j plus a half k plus a half. So I should have drawn this figure larger. Let me go in somewhere else. So Hy is defined at I plus a half j k plus a half, and Hg is defined at I plus a half j plus a half. Okay. So this is a little bit complicated, so I'll give you 10 seconds to look at this figure, and if you have any questions, please let me know.
Who is the person he?
Oh, he's the person who developed this script.
Right. Where is the person from?
He was a professor in UC Livermore, I think, and he was.
What? There's not a UC Livermore.
I don't know. The paper says it's UC Livermore or something like that.
Could be a
Lawrence, yeah, UC Lawrence, yeah,
Okay.
yeah. So sorry.
Livermore is like a shopping mall.
Anyway, he was a person in mid-90s, so he invented this E-script in 1966. So he was a pretty old guy, but
1966.
yeah.
Wow.
So maybe I should use this board because I don't want to erase this figure. So one thing to note also is that all the field components Ex, Ey, Eg, and Hx, Hy, Hg are evaluated at different locations. So even EX and EY are not at the same location. And E field and H field are of course at different locations. So this is very similar to the time case. So for the time case, I said that the E and H field are evaluated at different time steps. And similarly, spatially, E and H field are all evaluated at different locations. So, using this, consider the z component of this equation 4 here. This is the z component of the equation 4. Sorry. No, I wrote down equation 3, but I raised equation 3. Or I
You have this.
Yes, and then and we want to evaluate this curl. Curl of H, right? And this curl of H is added to EZ, which is here, right? What is the curl loop for evaluating the curl of H centered around this EZ point? That is the curl loop. I'll temporarily erase this. So we had an EZ here. And the curl loop, curl of H, to be added to EZ should be centered around EZ. So the curl loop is this. It's pretty bigger, so it is a little bit difficult to read. But this square, the center of the square is located at EZ here. Okay. So we have here, we have HY and HY and HX here and HX here. Yes.
Those notation with IGK, they indicate where the vector originates, right? At what point you evaluate the
actually,
vector, right?
it is the location of the vector. So it is not a vector from here to here. It is the E field defined at this location.
At that location.
At that location.
Oh,
They're not actually vectors, it's the magnitude of that component at
Okay,
that
got it.
point.
Yes. So we evaluate the curl loop. We evaluate the curl of H along this curl loop. And then let's see how we can write this update equation. This is
and J plus 1/2, right? K plus 1.
So this is going to be the most difficult,
IJK.
most complicated formula today. So this is the equation. So this xy, the first hy is this, right? You subtract this hy from this hy. That's the first quotient here. Yes.
We're going to talk about like what happens at the boundaries and how we decide which field goes out into like outside our physical domain.
Simulation domain.
Well, the like, you know, obviously at some point you
Yeah.
make a
I'll
full-
talk about that. Okay, that was a good question. And the second quotient, we subtract two hx fields, and the first hx is this one, and we subtract this hx from the first hx. We subtract this from this. So that's basically the call operation. So I'll give you 10 seconds again to simulate this. So in summary, so FDTD method summary. Update, then evaluate, so we first evaluate correlates on E3, and then use collaborates to update by equation 3. And then evaluate curl B and use and then we repeat this.
It's delta y on the second term in this brackets, right?
This one?
Yeah.
This is delta y.
And so you also define the Z component of current as same as what you did for E field, right?
Location-wise, correct. But the time-wise, it is defined at the H field location, H field time.
Okay.
So they are different. Okay. So there's the basics of FDTD. And let's talk about boundary condition. So I'll populate the east grid. I mean, I'll populate the space by east grid. So because 3D figure is too complicated, I'll draw 2D figures. And so each of these square is east grid at from the top. So you have EX here, and EY here. They're repeated. And this larger square is the simulation domain. And let's consider this row. So this is the enlarged version of one row of the grid, and we have EX here, EX here, and EY here, EY here, and HG here. And using the update equation to update this EY, we need curl centered around this EY, curl A centered around EY. This is this curl, right? And to evaluate this curl, we need this HG. This is not available. This is outside the simulation domain, so this HG is not available. But we need this to evaluate, update HY at the boundary. So let's say this is EY at the boundary, and this is HG inside, and this is HG outside. And I'll also call this HG far from this right-hand side boundary. And to update EY, the boundary, we need H component outside the boundary. So because this is not available, we need to make assumption here. So we either assume the value of Ey at the boundary directly, or assume Hg outside the boundary. So depending on the assumptions, we have several boundary conditions. So we can directly assume that Ey at the boundary is 0. Then you don't need the information about Hg outside the boundary. This is called PEC boundary condition. And
Perfect
Perfect,
electric
yeah.
conductor.
yeah. Or we can assume that AC out is actually equals to AC far. So we take this H value and use that here. That means we are assuming that this entire simulation domain is repeated to fill the entire space. That becomes periodic boundary condition. So and there are many other choices of assumptions to lead to different boundary conditions. Numerical has many other boundary conditions, but I'll not cover that here. Let me briefly show the